All right, hello everyone. I'm here for the lecture on convex sets, convex functions, and minimizers. And with me is Nate, who's going to help me out with this lecture and ask questions as we go along. Could you say hello, Nate?
Hi.
Excellent. So without further ado, let's get started. So today's lecture is going to be composed of three parts. The first part is on convex sets. We briefly talked about this in class on Wednesday. So I'll briefly go over that. I'll also talk about convex functions. This is now new material. And then I will discuss minimizers, the definition of minimizers. So let's get right into it and review convex sets. Now on this slide, I'm going to present to you what we discussed in class last Wednesday, and that is the definition of a convex set. So we say that a set denoted by D is convex if a line segment connecting any 2 points in D completely lies in D. And that's formalized into this definition here. So we imagine that D is some subset of Rn. By the way, D could be all of Rn. And then we also consider the scalar parameter lambda that varies between 0 and 1, which we'll see will parameterize our line segment. And then we consider any pair of points that's in this test set D, and we'll call that A and B. And a set is convex if it passes the following test. We will check for every single pair of points in D that the line segment connecting A and B, which we can write in this way where lambda parameterizes a point on that line segment, that any point on that line segment needs to lie in D here. Now note, of course, when lambda is 0, then that corresponds to point B. When lambda is 1, that corresponds to point A. And as we vary lambda from 0 to 1, that just moves us from point B to point A. Now, the way this definition works is we have to check this for all lambdas from 0 to 1. And then more than that, we have to check it for the infinite pair of points A and B that exists within this test set D. So one thing I want to emphasize now is this is fine as a definition. This condition, though, you might recognize is not so practical in terms of providing a practical test for our set, because you would literally have to check an infinite number of pair of points. So for now, just understand it as a definition. It is not a very effective way to check if a set is convex. It's just a way to define what a convex set is. Hopefully that makes sense. So on the bottom we have some examples. On the left we have a convex set. So one way you could imagine this is, Nate and I will pick places within the set D. We can pick any 2 arbitrary places, and whatever places that we pick randomly, we can always see each other through line of sight. In contrast, the set on the right here, it's easy to find 2 spots where we lose this line of sight. So we talked about some examples in class. For example, on the left here, we have this set given by this hexagonal-like shape. It is convex. In the middle, we have this set that is kind of this amoeba shape. So here I'm showing some example pair of points where we lose line of sight. Now this example here on the right is a bit more challenging. We did something similar on Wednesday. Nate, if you don't mind, I'm going to ask you, what do you think? Is this set a convex set or not?
It's not.
It's not. And then where would you pick the 2 points for which we could draw a line segment, and some part of that line segment would be out of the set?
2 points along one of the edges where that dash is in between.
Yeah, perfect. So for example, if I picked, let's just say, the upper left-hand corner as point A and the upper right-hand corner as point B, I draw a line segment between it. The part of the line segment for which I don't have this closed part of the set, that would in fact violate the definition. Okay, this is kind of a tricky case that you'll find in, exams, probably less so in applications, but is good to really test your knowledge. Okay, and that's what's described in this caption. So let's talk about a few more important examples. I mentioned some of these in class, but let's review. So an empty set, I didn't talk about that in class on Wednesday. The empty set or a single point, sometimes we call this a singleton, or the whole space Rn, by convention, well, at least for the empty set and the single point, by convention, we denote that as a convex set. Okay, so that's kind of this degenerate version of the definition. And then the whole space of Rn we'll call convex.
What is an empty set?
So an empty set would mean that the set D that I'm going to consider is just nothing.
Okay.
So just by convention, we'll say that's a convex set.
Okay.
Any line in Rn is convex. So for example, if I picked Rn to be R2, meaning a Cartesian coordinate system, you draw on a piece of paper, and then a line would be the x-axis. The x-axis will be convex. Any line segment in Rn is convex. Array is convex. So I've described it mathematically here. An example would be if I pick R2, like the two-dimensional Cartesian coordinate system, array would be, for example, the non-negative part of the x-axis, so the origin plus the positive part, that's array, that's convex. And a hyperplane is convex. So a hyperplane would basically be, well, in R2 would be a line, right? And then in R3, that is literally a plane in R3. So we live in a three-dimensional world. If I take this folder here, and it represents a plane in R3, this plane here is a convex set. And if I'm talking about Rn, where n is greater than 3, we cannot visualize this anymore. But a hyperplane would be given by this linear equality constraint. That's actually a crucial thing to recognize. It's a linear equality constraint. That forms a hyperplane, and the hyperplane is a convex set. So other important examples that are going to pop up as we get into applications later are going to be the half space. So this is actually a hyperplane, but we replace the equality constraint with an inequality constraint. So for example, in R3, I have this folder, and the half space represents everything on this folder and above the folder. So that divides three-dimensional space into two parts, the part that's above the folder, the part that's below the folder, and let's just say that the part that is the folder and above is part of my set. That's a convex set. And there's a picture shown here. The other example that we have discussed is the Euclidean ball. So the Euclidean ball is going to be parameterized by two things: the center of the ball and the radius of the ball, just a measure of how large it is. So for example, in 3 dimensions, the Euclidean ball will be a sphere. Okay, and in n dimensions, the Euclidean ball is going to be some hypersphere. And mathematically, we represent the Euclidean ball by this formula here. B we'll use to represent this Euclidean ball, which will have 2 parameters, the center and the radius. And we can write this as a set by saying the Euclidean ball is going to be all the x's in Rn here, but all the x's that are a distance r or less from the center. That's what this 2 norm means. And where distance is going to be measured by this 2 norm. And in fact, you can write this 2 norm in a form that looks more like a quadratic shown here. So these 2 representations are equal. So that's the Euclidean ball. The other example is an ellipsoid. So this is kind of a generalization of a Euclidean ball. It's not fully symmetric anymore. So again, this will be parameterized by the center of the ball, and then we're not just going to have a single radius. We're going to have something, a matrix that's going to encode how long our semi-axes are. So, for example, in 2 dimensions, an ellipsoid is just an ellipse. And then I'm looking around to see if I have a football. I guess I don't have a football, but you can imagine in 3 dimensions, a football type of shape would be an ellipsoid, right? So this is represented by this E in a calligraphic text here. And what this says is the ellipsoid is going to be given by x's and Rn such that this inequality holds. So you can see this looks almost like the Euclidean ball shown on the previous slide here, except now I have this matrix A, or the inverse of A, that essentially weights the directions, that weights how far I can move away from xc in each direction. And it turns out that A is going to be a symmetric and positive definite matrix, and A is basically going to encode the lengths of the semi-axes in each direction. Now, something that's particularly interesting and cool is that actually the eigenvalues of A give the lengths of the semi-axes. So if all the eigenvalues are the same, we just get our Euclidean ball. But if we have a football type of a shape, in one direction we'll have a shorter semi-axis, and the eigenvalue corresponding to that will be smaller. And then in another direction we'll have a longer semi-axis. The eigenvalue along that direction is going to be a bit larger. We'll see. Actually, you'll see an example of that in homework. Now, another common representation of the ellipsoid, which we'll use later in this chapter and you'll use in your homework, is what's shown in equation 4 here. So here what it says is the ellipsoid is going to be given by this expression, xc plus pu, where p is a matrix and u is a vector which has a magnitude less than or equal to 1. So here's how I want you to imagine it. What it says is we have a center for our ellipsoid given by xc, and then u, this is actually a unit ball, like a unit size Euclidean ball. Okay, so we have xc, and then we have our unit size Euclidean ball, so it's kind of our building block for our ellipsoid. And the role of P is it basically blows up our Euclidean ball, and it stretches it in some directions and maybe a little less so or more so in other directions, and it blows up that Euclidean ball into an ellipsoid. That's what it represents. So it's kind of a nice way to think about it. So again, xc is the center, u is this unit-sized ball, and then P is a square positive semi-definite matrix, which is going to blow up the ball into an ellipsoid. Okay, and then here's of course an image here. Importantly, remember the semi-axes are given by the eigenvalues of P in this case. Okay, and then the final important example to discuss is a polyhedron. A polyhedron is defined by a finite set of linear inequalities and linear equalities. So in equation 3 here, notationally we'll denote P by this a polyhedron by this calligraphic P, and it's going to be the set of x's in Rn, which satisfies some finite set of linear inequalities and a finite set of linear equalities. Now, Nate, you mentioned taking another class in optimization. You've probably talked about linear programs, right? And in fact, you recognize these are just the constraints associated with linear programs. Yep. So we'll talk in this class about linear programs later, but it turns out that the constraints for linear programs always form a polyhedron by default. And I can rewrite 3 in a vectorized form where I basically aggregate all the AIs, BIs, and AEQJs, BEQJs into these matrices and vectors into this form that starts to look like a linear program.
So for the other shapes, can different types of optimization problems be represented as those?
Yeah, in fact, what we'll see is that all of these will form convex programs. It turns out that when we have linear inequalities and linear equalities, when our objective function is also linear, that's a linear program. When our objective function is quadratic, that's a quadratic program. And then there'll be some other variations that I'll talk about later. Now, let's talk about the Euclidean ball for a sec. So this constraint is of a quadratic type. So that's not a linear program, as we'll see a bit later. It is not a quadratic program, but it is a quadratically constrained quadratic program.
Okay.
We'll talk about that later. And in fact, an ellipsoid is a quadratically constrained program. If our objective function is quadratic, we say it's a quadratically constrained quadratic program.
Right.
So that's why this is all important. It's going to all link up.
Okay.
Yeah, great question. All right, so the next example I'm doing at home here, where I have my pad, so we can draw. The next exercise is called square and disk. What we're going to do is consider R2, and we're going to define a square S, which is going to be given by the values of x1 and x2 that vary from 0 to 1. And then we define the disk to be the values of x in R2, for which the 2 norm is less than or equal to 1. And what we'd like to do is evaluate if the following statements are true or false. We're going to consider if the union of sets S and D are convex, if the intersection of sets D and S are convex, and if the set difference of D from S is convex. So next, I'm going to go into Photoshop here, where we can now draw this. So first I'm going to draw some axes. Whoop. Let's do it like this. All right. So here is R2. Alrighty, so we have x1 and we have x2. And then I'm going to draw some tick marks here. So we have 1, 1, minus 1, and minus 1, perhaps not in proportion. And then the square, S, whoops, is going to be given like this. Okay, very good. And now I'm going to fill in the square to be blue just to help us out. Very good. That's our square. I'll denote that square. And then we have our circle. All right, so this might not be to proportion, but our circle is going to be the values of x1 and x2 for which the 2 norm is less than or equal to 1. So basically, it's going to be a circle as follows. Okay, I am not an artist, so excuse me here. And this is the disk. In this case, it's a circle. So I'm going to fill that with red. Okay, very good. And then we have this overlapping region. Let's make that purple. All right, something like that. So now I'd like to consider first the set union of S and D, the square and the disk. So the set union is going to be given by the union of the square and the union of the disk. So we're basically talking about the red, purple, and blue regions all together. So we can see there that the resulting set is indeed convex. I can pick any 2 points inside my set, draw a line segment between them, and the entire line segment exists in the union of S and D. So let me, just for clarity here, let me say S union D is convex. All right, next we're going to consider the intersection of S and D. So the intersection is given by the regions for which the sets, the part of the sets that are in both S and D, and that's given by this purple region. In fact, I'll write S intersection D right here, and this is given by this sector. In fact, we'll see later that that's actually a second-order cone constraint. And that also, we can see by inspection, is a convex set. Okay. And then part C here is the set difference, S minus D, where minus is the set difference, meaning we're going to look at the square and take away from it the disk portion. So that is basically given by this blue region here. This is S set difference D, okay? And what you can see is this is not a convex set. Not convex, because I can pick 2 points on the set. In fact, let me pick these. Let me use a different color here. Green, why not? I can pick this point and this point, which is in set minus D. Draw a line segment. Draw a line segment between those 2 points, and there are portions of this line segment that are not in S minus D. So we can see that that is not convex. All right, so that completes our example of the square and disk. So let's now move on to convex functions. All right, so before we're talking about sets, and there's a notion for convexity for sets. Now we're going to talk about functions, and there's a notion of convexity for functions. Now it may seem confusing that we have the adjective convex for 2 different objects. They're actually intimately related, as we'll see later. So now we're talking about using the same adjective for a different type of object, namely a function. Okay, so keep in mind they're 2 different objects, but you'll see why it makes sense to use that adjective, the same adjective for both these objects. So the definition goes as follows. So first I'll kind of explain it graphically in a very intuitive way, and then we'll go through the precise definition. So a convex function basically means the following. If I have a candidate function and I pick any 2 points in the domain of that function, let's call it A and B, so x equals A and x equals B, and then I look at a line connecting, A comma FA, and then B comma FB, then that line there is going to be above the function. It's like that. So we can say this in a mathematical way that looks almost similar to the convex set definition as follows. So first, we're going to consider a convex set over which our function is defined. So for example, my function could be defined over all real numbers. And again, I'm going to consider the scalar parameter lambda that goes from 0 to 1, which will parameterize how we move from 2 points. And then we'll have 2 points A and B that'll exist in this set that x is defined over. So we say that the function f of x is convex on the set D if the following inequality holds. So what it says is, if I take A and I take B and I take a linear combination of them, where my linear combination is going to be given by the following expression, where lambda basically parameterizes moving, from B to A, as lambda goes from 0 to 1. And I evaluate my function at that value of x that goes between B and A, right? Then the value of the function is going to be less than or equal to if I take f of a and f of b and basically parameterize a line between fa and fb. That's the precise mathematical definition. And we need to check this for every single pair of points a and b in D, which is the convex set that X is defined over. Okay, so this is the mathematical definition of a convex function, and there is actually corresponding to it a concave function, which is in a sense the opposite. So this definition looks almost the same, except now when I take a line segment from FA to FB, this is going to be underneath the function. So if you look at this definition, it looks the exact same. The only thing that changed in equation 5 here is that this less than or equal to turned into a greater than or equal to. That's the only thing that changed. So we call this a concave function. Okay, now there is also a special version of a convex function called a strictly convex function. And what that means is that this less than or equal to becomes strictly less than. That's it. So we call that a strictly convex function. So, by the way, let me give you an example. A linear function would be a convex function, right? In fact, a linear function would satisfy this definition for every point, every pair of points A and B. It satisfies this inequality with equality. Right, because as we pick these 2 points FA and FB, we draw a line segment. That line segment just sits right on top of our function. A linear function is not a strictly convex function. Okay, these little notions become important later, but yeah, this is something stronger now. We need some sort of shape to our function. You can recognize that the second derivative will be non-zero. That's we'll talk about that a bit later. And similarly, a strictly concave function means that it satisfies this definition of a concave function, but with a strict greater than or equal to, as opposed to greater than or equal to. Okay, so let's discuss a few exercises to test our understanding. In these exercises, what you need to do is identify if these functions are convex, if they're concave, if they're neither convex nor concave, or if they're both convex and concave. And specifically, we'll consider x to be defined. Specifically, we're interested in these functions over the domain of x going from -10 to 10. Okay, and of course, x from -10 to 10, that's an interval, that's a convex set. Let's just go through a few of these. We won't go through all of them, just to test our understanding. So, yeah, hope you don't mind if I put you on the spot here. So, and we can use graphical arguments here. So let's think about the trivial function f of x equals 0. So what do you think about this? Is this convex, concave, neither, or both?
I would say that's both. That's a line, so it's has the equality of both concave and convex. Exactly,
precisely. So actually, whatever we give f, it just spits out 0.
Right.
So it's super easy to see any a and b from -10 to 10. It doesn't matter. F will just always spit out 0. So it's very easy to see that both these definitions will hold, and in fact it'll be 0 on both sides. So in that sense, it is both convex and concave.
So say the same for b.
So b is a linear function of x, and we can use graphical arguments. In fact, we were discussing linear functions before. F of x equals x is an example of that. And it's clear to see from graphical arguments that that's going to satisfy both the definitions for convex and concave functions. You can see, actually, the only way that the definition for convex and concave functions can be satisfied simultaneously, as if it's satisfied with equality always. Mm-hmm. And that is indeed the case for linear and actually affine functions also. Mm-hmm. Okay, how about C?
So C would be convex, while D, the opposite of that, is concave.
Perfect. Great. And we can actually, let me skip the next few. Let's go to H here. This is the absolute value of X.
I would say that is convex.
Yes. So that is convex. So if we can imagine here, actually draw it on the sheet of paper. Hopefully it shows up on video okay.
This one might work better.
Yeah, so we can see if we pick any points A and B. Draw that line segment between them. It's always above or on the function. And a good example of on the function would be as follows. Okay. I'll show that to you, Nate, so you can see.
Yeah.
Great. All right. The remaining I invite you to do as exercises as you study. Okay. A few useful properties for convex and concave functions. Actually, let me back up a sec and mention that in these exercises, it's all functions of a scalar variable x. X is not a vector. Let's now consider a function which takes as an input x, which could be a vector, n by 1. Okay? And suppose that x, we consider vector x over a compact set D, which actually is a generalization, or is a convex set. You can think of a compact set as a convex set. If f of x is convex on D, then minus f of x is concave on D. In other words, if I want to maximize a concave function, that's the same as minimizing a convex function, because I could define my new function as minus f of x, and minus f of x will be convex. Okay? Actually, what I described is in fact property 2. So we apply a minus sign to our function, and then we get the opposite with respect to concavity and convexity of functions. All right. Now, properties 3 and 4 are going to be the most useful in terms of being a testable condition. So I described before that the definitions, as I wrote them, are fine for defining what a convex or concave function are. These now provide definitions, properties that are more practically checkable. So it turns out that if f of x is a convex function on D, what that means is the second derivative of f, which, by the way, is going to be a matrix because x is a vector. And sometimes we call that the Hessian. Yeah. This is going to be positive semi-definite. Actually, I don't want to emphasize on almost everywhere. That's a technical condition that mathematicians worry about. But the Hessian of f is going to be positive semi-definite for all the x's in our domain. And that is a necessary and sufficient condition for f being a convex function. And in fact, we recall this from calculus, where in calculus we studied scalar functions. And when we take the second derivative of a scalar function, if that second derivative is positive, then it's convex, and if it's negative, it's concave, which is property 4 here. The way I learned it, I think it's part of the American system of education, is positive means you're smiling and happy, and that's what your function does. Did you learn it that way, Nate?
I do not remember. I don't think so.
You didn't learn it that way? Okay. Yeah, I learned it that way. So when you're positive, then your function is smiling, and it's convex. So this is the generalization of that, where positive, for matrices, is positive semi-definite. Side note, if f of x is strictly convex, if it's a strictly convex function, then the Hessian here needs to be positive definite, not positive semi-definite. And similarly for a concave function, if f of x is a strictly concave function, then the Hessian would be negative definite, strictly negative definite. So that's nice because we can compute the Hessian, we can take derivatives, and then compute eigenvalues. And there's our test. Okay, now next I'm going to give some examples. And again, this may seem a little dense while we're discussing these examples, but here's the interesting thing, is when we go to applications, we can use these functions as basically building blocks to understand convexity and concavity in our applied problems. So it is really useful to understand these fundamentals. It's like if you play music doing your scales. So we're going to consider these functions f, where for now we're going to consider that x is a scalar. So the quadratic function is a convex function on R for any a here that is non-negative. Okay? And similarly, it's concave for any a that's non-positive. So it's pretty easy to see if we take the second derivative of this function, then it's just going to give us a. And properties 3 and 4 correspond exactly to these inequalities that are shown here. So this is pretty easy to prove with the properties on the previous slide. All right, next, here at home, I want to talk about the exponential function, which is given by e to the ax. And we're going to show here that it's convex on R for any scalar a. So I'm going to go back to Photoshop here. And the function we're now talking about is e to the ax. And one way to show that this is convex with respect to x for all scalars a is to take the second derivative. So if I take one derivative, then I get a times e to the ax, and then two derivatives is a squared times e to the ax. Now we can see that this will be greater than or equal to 0 for all real values of a. In fact, a squared is always non-negative. It's 0 positive because it's a square. And e to the ax, recall that it has this sort of shape. Right? This is e to the ax, which is always positive for every argument x that you give it. Powers of absolute values. So it turns out that if we have the absolute value of x to the power p, so when p is 1, we already discussed that. That's a convex function. It turns out that for any p that's greater than or equal to 1, we'll get a convex function. But interestingly, when p is less than 1, then that's not the case. Okay, the next example is the logarithm function. What we're going to show is the natural log of x is concave on the set of all positive x. So to do this, let's go back to Photoshop, where we can write some equations. So here we're interested in the function f of x equals natural log x. We're interested in natural log. And we want to show that this is a concave function with respect to x positive. So to do this, we can take derivatives of f of x. Hopefully you recall that the derivative of the natural log of x is given by 1 over x, and then the second derivative of x is given by minus 1 over x squared. So it's easy to see for all values of x, this is going to be a negative number because x will always be positive if x isn't 0, and we have this minus 1, so it'll in fact be negative. Now, let me remind you of the domain over which logarithms are defined. If I were to draw the natural log function, it would look like this. And actually, you can see very easily that that is a concave function. But you can see here that it's defined for all positive x. So given that the log is defined for all positive x, and the second derivative is strictly negative for all positive x, we have shown that the natural log here is a concave function. Okay, there's a term called negative entropy. This comes up in applications of statistics. Turns out that that function is given by x log x. Turns out that you can prove, and I'll leave that as an exercise, that that's convex on the set of all positive x's. So basically these are exercises in just taking derivatives and seeing under what conditions is the second derivative positive or negative. Okay, so these are examples with multivariable functions. So now we're going to consider that x lives in Rn. So f is a function of a multivariable quantity. Every norm is convex. So norms are basically distance functions. So if I consider some n-dimensional space and I want to measure distance in some form, that function that maps a point in n-dimensional space to some distance, it's always going to be a convex function. The max function turns out to always be a convex function.
Is that just a point on the function?
Is it a point on the function?
The max function.
Yes. So let's. Well, okay. So imagine that x lives in R2. So we have a vector that's x1 and x2. And we just want to find the maximum between x1 and x2. So it turns out that that's a convex function. In fact, the max function is the infinity norm. That's actually one of the norms. It's an infinity norm. So actually, the max function is a special case of that first bullet point there. So what it says is I'm in an n-dimensional space, and I just want to find, I have a point in this n-dimensional space, and I want to measure how far I am from the origin, and I want to find along which dimension am I furthest from the origin. Okay. So it's like that. Okay, the third bullet point, actually this is going to be important in your homework, as it turns out, is the quadratic over linear function. So if x in this case, x and y are actually scalars. X squared over y is a convex function over all positive x and y. So you can in fact take find the Hessian of this function where we have two optimization variables, x and y. So you're going to have a 2 by 2 Hessian, and you can go through that as an exercise and show that when both x and y are positive, then it turns out this quadratic over linear function is a convex function. Next, log sum exp. Okay, these seem kind of weird and arbitrary, but I'm telling you, I see applications where these pop up. So if we have this function that is this weird combination of things, where first we have, okay, x is a vector, x1 to xn. what I'm going to do is for all the x1 through xn, I'm going to take the exponential of those. Then I'm going to sum the exponential of those and then log it. Turns out that that's a convex function over Rn. Now, if you're taking the course in our department CE264, that's on discrete choice models. Are you taking that course, Nate?
I'm not.
It turns out that there's something called logistic regression that's used to understand, among other things, how humans make choices. It turns out that that form shows up exactly. It shows up exactly. I mean, it may seem totally arbitrary, but this is common in logistic regression and machine learning. One example is in discrete choice models. Okay, the next example is the geometric mean. So you recognize the arithmetic mean means I'll sum up all my components of x and then divide by n. The geometric mean says instead of summing over all the elements of x, I'll take the product of all the elements in x. And then instead of dividing by n, I'll take it to the power 1 over n. So we call this the geometric mean. It turns out this pops up in some design problems where we're dimensioning systems.
It's in calculating inductance for wires.
Yeah, you know, it shows up in calculating inductance for wires where we're looking at the equivalent inductance from a circuit. Yeah, there's that's a good example. I hadn't thought about that example. So it turns out that the geometric mean is a concave function when all the elements of x are positive. And the last example I'm going to talk about here is the log determinant of x, where x is not a vector. In this case, x is going to be a matrix. That's why I'm using a capital X here. And when x is positive definite, then it turns out that when we take the log determinant of it, that is going to be a concave function. Now, okay, where does this pop up? I think in the notes I briefly discussed this. In my own research, I've really exploited this property. So it turns out if you're doing something called optimal experimental design, meaning you're trying to optimize the physical experiments that you're doing to make your data maximally informative, it turns out that that expression will be crucial. And knowing that you have this concavity property means that you can do convex optimization. This is actually game-changing. It seems like a tiny little property that you see in a textbook and is not useful. It can be game-changing for optimal experimental design. Okay, again, so these are now operations that conserve convexity, so additional properties. So suppose that we have, we want to build a function that is a composition of all these little convex or concave functions. Can we compose together a big function that is convex or concave? How do we understand that? So it turns out that if you take a linear combination of convex functions, so for example, f1 through fm, all those fi's are themselves going to be convex functions of x. If I take a weighted linear combination of them, where all these alphas, these scalar multiples here, alpha i's, are greater than or equal to 0, that aggregate function is going to be a convex function. Okay? So if I want to prove that f of x is a convex function of x, basically I just need to check that all my weights here are non-negative and all my individual functions here are convex themselves. All right, let's now talk about the pointwise maximum. So consider f1 and f2 to be convex functions on some set D. Then we say that their pointwise maximum f is defined as the following. So f of x is going to be the maximum value that either f1 or f2 takes. Okay. Now let me move over here to Photoshop to give you an example. So let's consider two convex functions, f1 and f2. And let's use for f1, let's use x squared, And for f2, let's just use x. So now, if I draw some axes here, do my best to draw them straight. Okay, not bad. And now I'm going to draw f1 and f2. So f1 is going to be a quadratic, so it'll look something like this. Okay. And then f2 is going to be a a linear function that goes through the origin as follows. Okay, so if we label this, we have f1, which is the quadratic function x squared, and then we have f2. All right, now, the pointwise maximum is going to be given as follows. Let me use a bigger stroke here. Okay, it's going to be given by the values which are maximum as we move along x. So you can see, actually maybe I'll just highlight like this, that the pointwise maximum is given by this highlighted yellow portion here. And you can see indeed that by inspection is a convex function. So just to be super duper clear, let me now annotate that this yellow part is the pointwise maximum of two convex functions, f1 and f2. Alrighty, so that is the pointwise maximum function. That is a convex function if the component functions f1 and f2 are convex functions over D. Okay, and then the final one to discuss here is the composition of two functions, but the inner function is affine. Okay, so the two functions that we consider are f, where f is a convex function, and the argument that I'm going to feed into f, that's going to be the input to f, is going to be this affine function of x. Okay, so when I take my affine function of x, call it ax plus b, and then on top of that I apply this convex function f, then this aggregated function g is a convex function. So the composition of a convex function on top of an affine function, that is going to be convex. And similarly, if f here is concave, and then my inner function here is still affine, then g is going to be concave. Now, you might ask, okay, what if I fed into f, let's call it h of x, where h is a convex function. I take a composition of a convex function on a convex function. That is not necessarily convex. That is not necessarily convex. Similarly for concave. Okay, so it's a fun exercise in chain rule to test that.
So is the purpose of understanding which functions and sets are convex, so is the purpose of that so that we can just identify if our systems or problems are convex or not?
Yeah, that's exactly what's going to happen. Okay. Is we're going to, in the upcoming lectures, we're going to talk about different types of optimization problems. Mm-hmm. And as I mentioned in lecture, there's a whole zoology of optimization problems out there. And part of your job is to recognize what kind of animal you have,
right,
which basically comes down to the functions that describe the objective function and the constraint functions. Mm-hmm. Are they convex? Are they affine, etc.?
So does it matter which of these it satisfies, or is it convex or not?
So as I'll discuss later, we need all the function f, well, I'll discuss in a later lecture what properties you need on your functions. I'll say it quickly now. So if we have minimize f of x subject to g of x less than or equal to 0 and h of x equals 0, it's a convex function, convex program if f and g are convex functions of x, and if h, the equality constraint function, is an affine function of x. We need to show those, and then we know it's a convex program. Now, under more strict conditions, under f, g, and h, it's going to be a linear program or a quadratic program or a quadratically constrained quadratic program. We'll also discuss a special type of convex program called a second-order cone program, and those will be more strict conditions on f, g, and h. But the difference between a convex program and a non-convex program basically amounts to showing that f and g are convex functions and h is an affine function. Spoiler alert for what's coming next. And identifying that, it'll be useful to understand all these properties, because we might need to understand, is f a composition of all these little convex functions? So, did that answer the question?
Yep.
Cool. Great. So the last thing I want to talk about is what is a minimizer. So a few lectures ago, I said I wanted to be very precise about what it means for x to minimize an optimization problem. So now we're going to be precise and describe the different types of minimizers that can occur in our optimization problems. So the first type of minimizer I want to define, there's two that we'll define, global and local. The first that I want to describe is a global minimizer. What is a global minimizer? So we're going to say that x star, which exists in our set D, is a global minimizer of f of x on the set D. If f of x star is less than or equal to f of x for every single x that's in the set D. In other words, Nate, you give me an x star, and I test every other x that exists in D, and when I put that into F, I can find, I can't find another x that is better. It may be equivalently good, but it's not better. So, in other words, x star minimizes f of x everywhere in D. This is why we call it a global minimizer. It's global over D. In contrast to that, we have a local minimizer. Intuitively, you can understand what's going to happen is in some local neighborhood of our minimizer, it's going to minimize f, but elsewhere, somewhere far away, there could be another x star that gives a lower f. So the way we describe this mathematically is consider x star that exists in our set D. We say it's a local minimizer of f of x on D if, okay, it's going to get a little wonky, but let's walk through it slowly. We're going to consider there exist, this backwards, E means there exist in mathematical language. There exists epsilon, which is some positive scalar. So some small positive scalar where I need to show that f of x is greater than or equal to f of x star. Sorry, said backwards, reading left to right. F of x star is less than or equal to f of x, where x, I'm not going to check for all the x's in D. I'm going to check only in some local neighborhood. So let's break down this definition. I have actually the intersection of two sets. Let me talk about the second part here of the intersection. Basically, I'm looking here at all the x's that are within a Euclidean ball of size epsilon away. Actually, it's not, so the Euclidean norm would be the 2 norm. I can pick any norm. I can pick a 1 norm. That would be like, instead of a Euclidean ball, that would be a hypercube. Basically, I pick any x's that are no distance, that are a distance of epsilon or less away from x star. So that's how I formalize a local neighborhood. Now, importantly, if I think about some x, so imagine x star is actually on the border of my feasible set. Then if I pick an x that's outside my set D, it may be epsilon away, but then it's in feasible, right? So that's why I take the intersection of D and this norm ball here, right? Is because I'm actually going to cut it off to only the x's that are feasible. That's what that means. Okay, so this is a local minimizer. What it says is there's just some local neighborhood where x star minimizes f, and it doesn't say anything about there could be an x far away, which is better in the sense of it finds a value of f that is less. Okay, so here are some pictures just to demonstrate, very easy to see this. So let's start on the right. We can see that when x equals 9, this is a global minimizer of my red function f of x here. If I look at this function over here, which has a more interesting shape, if I look at where x equals 4, I can find some epsilon, let's say 1, right, where now I want to consider all the x's that are distance 1 away from 4. So basically x from 3 to 5. And if I look at all the values of x from 3 to 5, and I plug that into f, then I'm going to get a value that's the same or higher. So now I found an epsilon for which locally it minimizes this function. However, it turns out that further away there's another local minimizer, x star equals 8. And it turns out that for x star equals 8, that gets a lower value of f than x star equals 4. Okay, so these are both local minimizers. And if I'm considering x over the domain shown here, then 8 would be the global minimizer.
So if you do that and you consider the domain from 0 to 8 or 10, can you solve that now? Isn't that a non-convex problem?
Yeah, so you kind of stole my thunder for what's coming up next. No, it's great. You can see that, I mean, you're asking the question, why is it that sometimes we have local minimizers that might not be the global minimizers, and sometimes we have local minimizers that are also the global minimizers? Mm-hmm. And because we just talked about convex functions, it's very natural to see, well, it seems if my function is convex, then a local minimizer is going to be a global minimizer. That's exactly it. So if you have a convex function, you know that if you find a local minimum, it is also the global minimum. Super convenient, super convenient. So if you have some algorithm and there's some proof out there that says with this algorithm it converges to a local minimum, if your function is convex, then you know you can do no better. There is no other minimizer out there that's better. However, if you have an objective function, f of x, that is not convex, now you can solve some sort of optimization program. And typically, we use solvers that are of the type where they converge to local minimizers. Then we know that if f of x is not convex, it'll converge to a local minimizer, but there may be some other value of x star out there which has a better solution, right? So that's also why it's useful to be able to recognize if we have convex functions or non-convex functions. It's the difference between knowing if our minimizer is global or only local. By the way, in applications, let me just highlight, people might get a little too dramatic, I think, sometimes about needing to have convex functions. In many applications, if you can show that your design is locally optimal, sometimes that's really great. And you can implement that and have great impact. Mm-hmm. So it's okay to have non-convex functions sometimes. All right. And actually, that's the last slide of this lecture. Any other curiosities or questions that have come up?
The one question I had was about determining convexity for, what was it? It was like the geometric mean. Graphically, what would that look like? I guess when I think of mean, I think of a single number.
All right, this is an excellent question about the geometric mean. Let's do an example of a geometric mean. So I'll flip over to Photoshop here where we can draw some equations. All right, so this is a geometric mean example. So let's consider x being in R2. So the geometric mean in R2 is given by the following, well, in n dimensions, it's given by the following formula. And in R2, that is literally x1 times x2 to the 1/2. So what I'd like to do next is actually jump in MATLAB and make a surf plot, make some sort of 3D plot that's going to look as follows. We'll have x1 and x2 here, and then we'll have y or f of x specifically, which shows the geometric mean. All right, so here we are in MATLAB. What I'm going to do now is define x1 to take on values from 0 to 10, let's say, and suppose we do 101 values. Okay, so you can see here that x1 and x2 are values from 0 to 10. All right, and now I'm going to compute the geometric mean. So to make this really straightforward, I'm going to do this in a nested for loop. So it'll look as follows. I'll have a nested for loop where yi, comma jj is going to be given by x1 at index number ii times x2 at index number jj. And then we put that to the power 0.5. Voila. And now we can do the surf plot, this 3D plot. All right. Now here, you can see very elegantly, we have the geometric mean. So on one of these axes on the bottom, we have x1. On the other, we have x2. And the geometric mean is given by the vertical axis here. So what it says there in the slide is the geometric mean is always a concave function, and you can see that very clearly if we pick a pair of points on the plane on the bottom there, evaluate the geometric mean, and draw a line segment between them. It's going to be underneath the function. So that's a visualization of what the geometric mean looks like in 2 dimensions. All right, anything else?
No.
Okay. Well, great. Well, great. Thanks, everyone, and I'll see you in class next time.